This conference will
Maybe
now be
we'll kind of
recorded.
start with that tonight. Again, I'm still figuring out the software. Is the first time I've used it, so we'll kind of use it, and then we'll use feedback tomorrow. I'm going to share a screen once I start getting some questions rolling. I'm going to assume that you guys can see the chat box, but I guess I'm not sure. Can somebody like test something in there? All right, so Dominic says, yeah, it's working. Got it. Can you guys see a video feed? I'm not sure if I'm sending a yeah, I don't think that's working for some reason. Okay. I don't think the webcam is going to work for some reason. I don't know why. I'll have to figure that out. In the meantime, I want to make sure that I can share a screen. I can make the screen live. Like I can change what screen I'm showing. So right now you're probably just seeing like a generic screen. I'll turn something on just to show it. All right, so I just started sharing like just a browser. So I'm assuming you guys can see that. Just let me know if you can. Okay, so why don't you guys queue your questions in the chat, and I'll bring up an appropriate screen. I can bring up like a whiteboard and just do that if we wanted to do practice. If you have specific questions from like, you know, either an online quiz that we took or like a PDF, like a worksheet that we worked on in class, then I'll switch over to that. So let's see here. One of the questions was for the graph practice packet we got in class last week. Are the answers online? I think you're talking about, it doesn't show me who asked that question. But if we go to assignment 1.8, there were like 6 graphing practice problems, and right now I'm bringing up the graphs of motion answer key, so you should be able to see that once it pops open here in just a sec. So it was posted, the answer key was posted under assignment 1.8. So Dominic asked a question about the what's covered on the quiz. It covers everything from the beginning of the class, including some work like unit conversions, sig figs, kinematics terms, all the way up to before, like it includes kinematics in one dimension. So problems using the Galilean equations to solve for accelerated motion, but it doesn't include 2D kinematics like the horizontally fired projectile we started at the end of last week. So Dominic, make sure that I answered your question about what's covered. I'm going to get to Chris's question in just a sec, who said, let's talk about just do a graph of motion problem. Bear with me for 1 sec while I figure this out. Okay, so on the screen now are the solutions to 6 practice problems. No, this one's just 2. That's not the one I'm thinking of. I posted 6 practice problems. Oh, this one is just the one that's got 2, I guess. Let me find a different one. Bear with me. I did assign that earlier and reposted it for extra practice. Let's see if it's here. Yeah, that's the one I'm talking about. There's the document with the 6 graphs of motion on it. And the solutions are here under assignment 1.4. And so if you click on that, this is the answer key for those 6 questions. So, we could just kind of get things warmed up and do one of these practice problems right here. It doesn't matter which one we start with. Let's go ahead and start with number 2. Because Chris was saying, hey, why don't we just do a graph of motion question? So in this question, you're given a velocity graph, and you're asked to figure out what's going on up here in the position graph, and then you also have to fill in the acceleration graph underneath it. For starters, by definition, acceleration is the rate of change of velocity, or kind of an easy way of thinking about this is it's the slope of the line. So when you're going downwards on these graphs from velocity to acceleration, you're finding slope. So if you just take a look at this first line segment right here, we can see that it starts at 0 and ends at 2, or at least it's kind of supposed to. And it takes 2 seconds to do that. So if you were to do a rise over run calculation, or change in y over change in x, I'll just write that off to the side. M is equal to change in y over change in x. In this case, it's plus 2 over 2, which gives us plus 1. And so the slope is a constant 1 during that time interval. So that would be the acceleration graph. For the next segment, which I'll just do in a different color, for the next segment right here, we can see that the rate of change is 0. It's a horizontal line. So I'm going to use my open circles, and I'm going to drop down here to 0 because there is no acceleration. That horizontal line isn't changing. For that same reason, I could say here during segment 3 from 4 to 7 segments, 7 seconds right here, that also has no change. And so therefore the acceleration, which is the rate of change of velocity, is 0. Finally, this last one, you can see that since it's increasing, the slope here is going to be positive. A lot of students will kind of mix this up, but I think you guys have seen enough of these now that you probably won't or shouldn't. But keep in mind that that even though this is negative, it's below the time axis. So we're kind of down here in the negative region. Technically, that's a negative displacement, but the slope is still positive. So the change is +2. I'm going to write this out as change in y over change in x. But keep in mind that the change in y is, I could write that as y final minus y initial over the time interval. And y final in this case is 0, and y initial is -2. And 0 minus -2 is +2 over that 1 second. That's going to give me a rate of change of +2. So the acceleration over that last interval is +2. Are there questions, Chris, on the and others? Are there questions on filling in the acceleration graph, kind of this starting point that we did here? Now that we've done that, then the usual follow-up is to figure out the displacement, and that tends to be a little tougher. And when you're going upwards on these graphs, you have to find area. So the area of region number 1 tells us the displacement, assuming that we start from 0. By the way, I think this is more challenging, going upwards on the graphs and finding areas or integrals, if you will, than going downwards and finding slopes or derivatives. The area here is that of a triangle, so you can kind of make that out. You'll use 1/2 the base times the height. The base is 2, the height is 2, that's 4, half of that is 2. That means if we start at 0, we're going to end at position 2. And you'll remember doing these in class, we're either going to have concave down like that, or we're going to have concave up. And so we have to figure out whether it's the upper curve, which I'll call curve 1, or the lower curve, which I'll call curve 2. I'm going to give you guys a second or two to kind of decide which one you think that's going to be. Okay, hopefully you chose curve number 2. So I'm going to come back and sketch that in. We're starting at 0 and we're ending at 2. And the reason that it is curve number 2 is that since we're getting faster, the slope of the tangent line, or the line that just touches the function, is getting steeper and steeper. So notice we could do kind of a test. We could say at the beginning, the slope of the line is fairly small and positive. Let's call that 1 plus. And the slope of the position graph is velocity. So it's initially small and positive. Then the slope of the tangent line starts to get a little bit larger. We'll call that 2 plus. And so at some midpoint in the function, we can see that the value of the velocity function is increasing. And then finally, at the very end of the interval from 0 to 2 seconds, we can see that it's got a large slope. Let's call that 3 plus. And that's where we see the maximum value of velocity during the interval 0 to 2 seconds. So, for starters, the area under this graph is what gives us our displacement. It doesn't tell us where we are, it just tells us what our displacement is. So the displacement during the interval 0 to 2 seconds is +2 units. Let's take a look at the next interval, which is 2 to 4 seconds. The height is 2, the base is 2. That means our displacement is +4. That means if we started at 2, we're going to end at +4 units. We're not going to end at position 4, but we have to go 4 units beyond position 2, which means we're going to end at position 6. So I'll label that in here as position 6. That's going to be linear connecting 2 and 6 because the velocity was constant. We can see here that the velocity was not changing over the entire interval. Then from 4 to 7 seconds, we have 3 seconds, and so we can find the area of that interval right there. Notice that since it's below the time axis, the displacement is going to be negative. I have -2 over 3 seconds. That's going to be -6. So what that means is if I start from 6, I have to end at 0. And so this guy comes all the way back down to where we started from. And that's because this is negative displacement. Finally, the last area here is 1/2 the base times the height, or -1, which means that if I started on 0, I have to end at -1. And the slope of this one, think about this for a second, is going to be concave up or concave down. I'll give you a couple seconds to think about that. All right, it's going to be something that looks like this. It's going to be concave up, and we're going to use a similar kind of approach that we did in kind of region 1 over here. The slope of this is initially large and negative. Let's call that 3 negatives. We can see that the function begins at its most negative point. And when it ends over here, it's almost 0 or very slightly negative. And we can see that that's consistent with what's happening on the velocity graph. Please just type in if you have follow-up questions based on that, dusting off the cobwebs on that graph of motion. Okay, I'm getting another question about going over the difference between vector and scalar quantities. I'll make a list. I think that's kind of an easy way to go, and just be as forthcoming as I can. Let me bring up a different screen. I'm just going to write them out. I think that'll be the fastest way to go. So we'll make a list of vector quantities. Some of the kind of more important vectors that you should remember are velocity. That's obviously a huge one. And you know what? Off to the side over here, I'm going to write its scalar equivalent. So the scalar equivalent of velocity is speed. Sometimes you'll see this written as just like v, and your instinct is to say, well, isn't that velocity? But velocity has the vector hat on the top. So these are just, it seems trivial, but these are important distinctions in physics. Acceleration is definitely a vector quantity. Force is a vector quantity. We haven't studied force, but we will soon enough. And so those are really big vector quantities, the 3 that I've written. Another important one is displacement. Displacement is abbreviated with the delta character and then either x or y, or for that matter, it could be z. Let's just use delta x more generically. The scalar equivalent of displacement is distance. So if it doesn't matter how far you went, in what direction you went, you would use distance instead of displacement. Remember, the displacement is a vector, so your answer would involve, at a minimum, like a plus or a minus sign. Let's keep going. There are maybe a few others we should think about. For now, these, with the exception of force, are the big ones in kinematics. There are some other vectors that we'll talk about in the course that you don't need to know right now. Some other scalar quantities that are kind of more generic, like, temperature is a scalar quantity. Mass is a scalar quantity. Mass would just be, measured in units of kilograms, abbreviated with m. It doesn't have a direction. It's just a certain amount of stuff. So I think that would be a good list to just keep in mind. I could keep going, for basic things like time, typically lowercase t, but these are all scalar quantities. They don't have a direction associated with it. Emily, make sure that I've answered your question. Chris followed up with a question and said, are the things that we did in class today, Friday, going to be on the test? No, vectors are not covered by the test, not covered on the test. Today we did like vector resolution, resolving vectors into its x and y components, not included. And the horizontally fired projectiles, or the 2-dimensional kinematics problems that we did on Friday, also not on the test. Josh is asking about kinematics problem, and Dom is saying he wants to check again. Everything in 1D is on the quiz, or up to a certain number. No, content-wise, everything in 1D and kinematics in 1 dimension is fair game. And earlier up here, Austin asks, hey, what's up when they're just words and no pictures? There's an easy way how to figure out how to solve these kinds of problems. And I think that's consistent with some of the practice that people are asking about, like Josh and Dominic. So why don't we do one of these, and then we'll come back to a few other questions. So let me open up, or let me just kind of clear this stuff. All right, I'm going to start with just a question that might be written out, and then we'll kind of work with like how to deal with that. So we'll say that a sprinter starts in the blocks and accelerates from rest when the gun goes off to 6 meters per second over the first 10 meters. So question part A is going to be, what is the sprinter's acceleration? Okay, so you're going to see me in class, especially later on when we start doing forces. I'm going to really recommend that you make pictures, that you actually kind of like sketch things out. It really does help understand a problem. You know, right now, this is just like words, and you're not, you know, the art of being a physics student requires you to make like a mental model of what's happening, and then eventually, once you understand what's happening, you make a math model for what you're seeing. And so, you know, it wouldn't be crazy. This is going to kind of be a stick figure that I'm drawing. So you know, here's the starting gate here. The guy's getting ready to go, and then this is, you know, the first 10 meters. So he's starting from rest here. That's at position 0, and this is the finish line at position 10 meters. And you know, even though this is kind of a lame stick figure sketch, you know, for some people, it helps them see things more clearly. And then I could write things like, okay, the initial speed is 0 here at the starting point. We know the displacement, and so you know, we're looking for the acceleration. So I know VO. I'm looking for A. I know that delta x is equal to 10 meters, and I know that V final was given to me in the problem right here. It's 6 meters per second. So V initial is 0, V final is equal to 6 meters per second, and the displacement is equal to 10. Well, the kind of recommendation that I've made is that you identify one of the kinematics equations. These are the Galilean equations to help you solve the problem. When I look at this one, it looks like the third equation, which looks like this. And if you were solving this problem on an FRQ, you're going to get points for writing it out. V final squared equals V initial squared plus 2A delta x. So just writing that out, even if I didn't finish the problem, is going to earn me some points. So the second step would be to really solve this for A, develop an expression for A. That's going to be V final squared minus V initial squared divided by 2 delta x. And now I have an expression for A, and I'm ready to substitute some numbers in. V final is 6 meters per second. I have to remember to square it. V initial is 0. And then I'm going to divide that by 2 times the displacement of 10 meters. So that's going to give me 36 in the numerator, half of 36, because I'm dividing it by 20, or I could divide it by 2. Half 36 is 18. Divide that by 10 is 1.8. So it looks like my acceleration is 1.8 meter per second or meter per second squared, 2 sig figs. You know, I wish there was like a kind of a golden bullet where I could just say, hey, you know, all problems can be solved this way, and this is the easiest way for everybody to do it. I can't really do that. I guess what I would recommend, you know, a couple of things to keep in mind are A, make a picture. Actually, let me change the color here. Make a picture. The picture is important for some people, not everybody. B, write down what you know. I strongly encourage you to do that, to kind of write down the 3 things that you know, the one thing that you're looking for. C, write out your starting equation. In this case, I used the third kinematics equation, but I actually took the time to write it out. A lot of kids don't do that, and if you make a mistake, then all you have on your paper is kind of like, well, I don't want to call it garbage, but you don't have anything to present. If you didn't even write down a starting equation, and let me give you an example of a poorly kind of solved problem. Let's say a student didn't follow this path. You know, I guess what I'm trying to do is say, okay, if this is considered good problem solving, then let's make like, you know, a sketch of like common mistakes that I would qualify as poor, or, you know, not bad, but needs development, needs improvement. So it might look something like this. If I were solving this, these are things that I would avoid. A student might read this question and then just write something like this. All right, so the final is 6. I'm going to square that, and I'm going to set that equal to the initial squared, and I'm going to add to it 2a and 10 meters. So a couple of things here. There are no units. There are units over here, but not over here. I'm not even really sure as an evaluator like what's going on here. And then the next thing a kid might write is, you know, a is equal to 4. And this, you know, that's not even an answer. So the sig figs are off. There are no units. The answer is wrong. And as an evaluator, I can't even really look at this and give it anything at all, not even a single point. Whereas if the question over here were worth, let's say, 5 points, you get a point right here for writing that equation. You get a point here for rearranging it, a point for substituting it, 2 points for the answer and the correct number of sig figs in proper units. All those things add up, and the kind of, you know, the needs improvement answer on the left-hand side doesn't have any of that stuff. Hopefully that's helped. A couple of other questions. Ryan's asked a question about a displacement problem. I'm not sure if I answered it here because we did a problem with displacement, and we did a previous graphing problem where we had to kind of fill in the position graph from the velocity graph. So Ryan, follow up with me and let me see if that helped. Aiden asks, how many questions are on the test? You're going to have 10 multiple choice questions. I would say that the 10 multiple choice questions are challenging. There's very few like just give me problems. So let me kind of write out the format here. So 10 multiple choice. These are worth 2 points each, and so that's a total of 20 points. And then there's 2 FRQs. There's like one easy FRQ that involves some unit conversion maybe, and then like some basic kinematics that, let's say, that's worth like around 7 points ish. And then there's maybe one what I would consider harder free response question that might be worth, let's say, 15 points, or let's kind of make this easy here. That's 13 points. So now we're at 40, and then there might be just one straight up graphing problem. Although there might be some graphing problems in here, but just like one, you know, you're given something like position, velocity, and acceleration. You have to fill in the other ones. And that might be worth around 10 points for a grand total of around 50. Aiden, make sure I've answered your question. Riley asks a question on the 1.5 practice quiz. I'll take a look at that, and then And then somebody also asked about a problem like the rocket one we did in class, which I think would be a good idea to kind of go over that. Let me bring up assignment 1.5 and we'll take a look. All right, let's see here. All right, so there was a question that asks, what's the magnitude of displacement between 2 and 4 seconds? I think it's this one right here. Riley, make sure this is the one that you wanted me to review, and we'll kind of go over this one. All right, so that's the one. Give me 1 sec. I need to make this bigger and not quite sure what the best way for me to do it is. How do I make the screen bigger? Is it Control plus Shift? What's the, let's just do that. That'll work. Okay, so on this graph, we're asked about the magnitude of displacement from 2 to 4 seconds. Keep in mind that this problem, one of the things that I recommend is that the first thing you do when you get a problem like this is you very quickly make sure that you're dealing with a velocity and time graph. If this were a position graph or an acceleration graph, we're going to get a really different answer. So since I'm asked about displacement and I have a velocity versus time graph, I know that I have to find the area under the graph. And so since I'm only going from 2 seconds to 4 seconds, I only need the area bounded by these blue vertical lines. So basically what I'm saying is everything bounded by the blue here is the displacement during the interval from 2 to 4 seconds. Now, I think the easiest way is to just recognize, well, I can kind of take the area of shape number 1, which is a triangle, and add it to the area of shape number 2, which is a rectangle. It looks like a square, but we have a scaling issue on the y-axis. The base is 2, right? Because from 2 to 4 seconds, the base is the number 2, and the height is 20. So I guess, we can say then that during that interval, we went 40 meters just for the rectangle. Now we have to add to it the area from the triangle, and that's 1/2 the base. The base is also 2. The height is 20 because I go from 20 to 40. Half of 40 is 20 meters. And so we can say then that the total displacement from 2 seconds to 4 seconds is the sum of these two. It's the total area under the function. And so the correct answer would be 360 meters. Riley, make sure that that I've answered your question. The rocket one that we did a week ago that you have to use more than one kinematics equation for, which somebody asked about, is linked to Josh's question about doing like a more challenging or difficult FRQ. So let's kind of take a look at a question like that. And then since it's 9:06, I think by the time we finish that, we should be pretty close to calling it quits. The rocket problem that that we did in class was, I would consider that a pretty challenging problem that a lot of kids are still going to struggle with. Even though we did that problem, if I were to put that on the FRQ, I would consider it one of the more difficult problems to solve. So let's do this. I'll make a variant of that. So we're gonna have a rocket, and while you guys are kind of waiting, it wouldn't be a crazy idea to make an attempt at solving this problem either off to the side or kind of on your own while we're discussing it. Maybe I'll give you guys a little bit of time to do that. So, I'm going to call this position 1. The rocket starts from rest on the launch pad. And then we're going to say that the rocket engine fires all the way to position 2. So there's a period of time. Rocket's not looking great. But there's position 2 of the rocket. And during that interval from 1 to 2, we'll say that there's a known acceleration of the rocket. It's going to be equal to 15 meters per second. And the rocket engine fires for 10 seconds. So then, if that's all we know, and then after 10 seconds, let's call that point right here, the engine cuts off. We know that the rocket's going to continue to coast. It's going to slow down, and it's going to eventually turn around and fall back down. But from 1 to 2, it's definitely still accelerating up, and then from 2 to 3, 3 is going to be the highest point that it gets. So at position 3, we can say that is as high as it gets, and we know, or we should know, that the velocity at position 3, at the very apex or the highest point that it's going, is going to be 0. So to solve a problem like this, and I'm not going to solve the whole thing, I just kind of want to talk about it a little bit. We recognize that in region 1, which we're going to call this the blast phase, the rocket is still accelerating upwards, getting faster and faster and faster. And then, so the acceleration here was given to us in the problem. In the coast phase, once the engine shuts down, in the coasting phase, the acceleration of the rocket is just going to be Earth acceleration. So A switches from positive 15 to negative 9.8 or negative 10, whatever you want to use. And so therefore you have 2 separate problems, and it would be fair to ask simply, given just this information, to ask the question, sorry, let's make that a Q, not an A. The question might be, how high does, what's the maximum height? How high does it go? Okay, so that's really what we're trying to solve. How high does this thing go? I think one of the great places to start is to recognize, what is the information that I have in the blast phase? Well, we know that A is 15 meters per second. We know that the time is 10 seconds. Let's make that 2 sig figs. I'll put a line over that guy. And we know that the initial velocity is 0. When it was down here on the launch pad, it started from rest. And really what we're looking for is, we can't solve phase 2 without knowing what this velocity is, right when the engine cuts off. Now, in question part 1, that would be the final velocity. But when we're dealing with part 2, which is kind of the second question we're going to have to deal with immediately afterwards, the final velocity from part 1 becomes the initial velocity for part 2. Those are the, that's kind of an important distinction to make. So once this thing reaches its final velocity for part 1, it's going as fast. It's not going as fast as, it's going as fast as it's going to go. The engine shuts down, starts to slow down. And so we kind of need to figure that out. That's a logical first step to take. We're going to answer that velocity question and then answer part 2. Based on this information that I have right here, I'd use the third equation. I know we used it earlier today. VF squared is equal to VO squared plus 2A delta X, in this case, technically delta Y. No, I wouldn't use that. Here's why. Actually, this is a good mistake to make right here out of the gate. We don't have 2 things. We don't have V final in this case, and we don't know the vertical displacement, so that wouldn't be a good choice. Why don't you guys take a second and see if you can figure out which equation to use. Somebody could also throw it out in the chat box whether they think the first equation or the second equation might be a better choice. Yeah, 2 is the right one to use. So we're going to get V final is equal to V initial plus acceleration times time. This is what we're looking for. V final, V initial is known, A is known, T is known. We're good to go. So that's just going to be 0 plus 15 meters per second times the time of 10 seconds. And so now we can solve this for VF, and it's going to be 150 meters per second. This thing's booking. So now that 150 is going to be the initial velocity for part 2. I'll solve all of that in a different color. Let's use this kind of like green color. So now we have the initial velocity, it's equal to 150. I wouldn't have known that had I not solved kind of the, step 1, if you will. A is Earth acceleration. Let's just call it -10 for now. It's technically -9.8, but we can use -10. By the way, the College Board permits you guys to use -10 in lieu of 9.8. Makes your kind of calculations easier and rounds them out. So that's A. We know V final is 0. We discussed that already. When it gets to its maximum height, it stops, and then it turns around and starts to come down. And we're trying to figure out simply how high it goes. So we would need then to answer this delta y. Now, here's the thing. That's only going to give us the delta y for part 2. So we're going to have to then go back again. It's almost like running in a complete circle. So we needed the VF from part 1 to answer how high it's going to go. And then that's only going to tell us this delta y, and we'll have to do it again for part 1. This is kind of almost like a 3-part problem. So now that we have that, the third equation makes sense to me. VF squared equals VO squared plus 2A delta y. I'm going to solve this for delta y. It becomes VF squared minus VO squared divided by 2A is equal to delta y. It's getting a little messy. So I think I'll just kind of clear all this stuff so we can see a little bit better. I know we can't see the sketch anymore, but it'd be V final squared is 0 minus V initial squared, which is 150 meters per second. I got to square that whole thing, and then divide it by 2 and -10. That's going to give me my vertical displacement. So 150 squared, I'm going to need a calculator for that. And then that's going to be divided by 20. I'm getting 1,125 meters is equal to the vertical displacement, but that's really only for that kind of second part. We're going to have to figure out the vertical displacement for the first part, add those 2 pieces together, and then we'll be done. So, I just erased my sketch, but I can kind of remember most of the stuff. I'll just, write down what I know. Again, we're solving for the height of the rocket during the blast phase. We know that it started from rest and that its final velocity was equal to 150 meters per second. And we know that the acceleration was given to us as 15. And we're looking for delta y. We can again use the first equation. I'm going to call this delta y subscript 1, the vertical displacement during that blast phase. And so I'll just again solve for delta y. I'm really doing the same thing that I did right here. And that becomes 150 meters per second. I got to square it and then subtract it from 0. That's the initial velocity squared. And then I divide it by 2 times 15 meters per second. And so I again get 150 squared. And I'm going to divide it by 2 times 15, which is 30. And I'm getting 750 meters. So it goes 750 meters during the blast phase. And then I'll call that delta y1. And then 1125. So it coasts further than it did during the blast phase. I'm going to add those 2 together to get the, the total height that it goes. And so that's going to be 1,875 meters. Now I got to deal with significance. This is the total Vertical displacement, I'd call that 1900 meters. So that would be an example of a kind of more challenging problem that you might see on the quiz. Ryan's follow-up question is, if you use -10, would it be 1 or 2 sig figs? It would still be 2. And I think that they write that on the like instructions. So they say that like you can use G is equal to 10. They probably write it like that, meters per second squared on the test. G, by the way, is assumed down, so you could say A is equal to -10 meters per second squared. G specifically means the acceleration due to Earth gravity, which is assumed in the downward direction. If one's numbers were slightly different, but they rounded to 19 because of sig figs, is it still right? Yeah, of course. And even if, let's say you kind of rounded differently and you had different input numbers and you ended up with the number 1800, the College Board definitely gives like a range of numbers that are considered correct. So that might even be acceptable without any deductions. Okay, I'm going to stop there. And if you have questions, you guys can see me in the morning, or the first class that takes this is in the afternoon tomorrow. So feel free to pop in. I would appreciate it if you have any feedback on how this session went using the software. Just drop me an email afterwards. I'd like to read through these tomorrow and kind of check it out. And if I missed any of your questions, I apologize. I think I got everyone's questions, so we should be good. So again, send me some feedback, some email feedback, so I can try to make some improvements for next time. That's it. Thanks very much. Have a good night.